Have you ever looked at a massive bridge or a skyscraper and just wondered how it can be so strong but also flexible? Well, today we're going to pull back the curtain and dive into the engineering of bending, the invisible forces that are literally shaping the world all around us.
Just take a look at this bridge. I mean, it seems absolutely solid, right? Rock solid. But here's the thing. It's actually designed to bend and flex all the time. So that brings us to the million-dollar question for any engineer. How in the world do you predict with total certainty exactly how it's going to bend before a single piece of it is even built?
And let me tell you, this is not just some academic puzzle. Understanding and being able to predict this bending, what engineers call deflection, is absolutely critical. It's the key to the safety and stability of pretty much every structure we use every single day.
I mean, think about it. If a beam in a building bends too much, it's not just that it might look a little weird or feel wobbly, it could actually threaten the whole structure's stability. And even worse, all the brittle stuff attached to it, like plaster walls or concrete facades, could start to crack and fall apart. The stakes are incredibly high.
So how do engineers even begin to tackle this problem? Well, it all starts with visualizing the bend itself. They have to imagine this invisible shape that the beam creates when it's under pressure. And that idea, that invisible shape, is the key to everything.
So engineers start with the beam in its perfect, unloaded state, just a straight line. But as soon as you apply a force to it, it deforms into this subtle curve. And that curve, the exact path it follows when it bends, is what we have to be able to predict with pinpoint accuracy. You know, this thing actually has a name. It's called the elastic curve, and you can think of it as the blueprint of the bend. It's this super precise line that runs right through the very center of the beam as it deforms. This isn't just a rough sketch. It's a real geometric shape that you can describe perfectly with math.
Now, the shape of this curve is determined right from the start by how it's supported. A pin or roller support, for instance, locks the beam in place so it can't move up or down, but it can still rotate. It's kind of like a hinge. But a fixed support, like a beam stuck deep inside a concrete wall, whoa, that's much stricter. It locks both the position and the angle. The beam can't move, and it can't even tilt at that point.
So those supports set the rules for the ends of the beam. But what dictates the shape of the curve in the middle? Well, the answer is in the hidden forces inside the beam itself. And lucky for us, there's a really simple way to picture it, as either a smile or a frown.
So let's get right to the heart of it. We know the curve is locked in at the supports, but what is it that actually makes it bend upwards in one spot and then downwards in another? What's going on there?
The secret is a force called the internal moment. You can just think of it as the twisting force inside the beam. When there's a positive internal moment, it makes the beam bend upwards, concave up, like a smile. And when there's a negative moment, it bends the beam downwards, concave down, like a frown. By figuring out this force all along the beam, engineers can literally map out the exact smile and frown shape it's going to take.
Okay, so what happens when a beam has a little bit of both? That exact spot where the internal moment hits zero, where the curve switches from a frown to a smile, or the other way around, that spot has a special name. It's called an inflection point. And finding these points is absolutely essential for drawing the whole elastic curve correctly.
All right, we've got the concepts down. The elastic curve, the supports, the internal moments causing smiles and frowns. So how do we stitch it all together with mathematics? Well, it's time to reveal the Rosetta Stone of beam deflection, the one formula that translates all these forces into a predictable shape.
The logic is actually pretty straightforward. It happens in 3 steps. First, all the loads on the outside, cars, wind, the weight of the beam itself, they create that internal moment, M. Second, that moment directly controls the curvature, basically how sharp the bend is at any given point. And finally, by connecting moment to curvature, we can write out the exact mathematical equation for the entire elastic curve.
And here it is, the big one, the moment-curvature relationship. This little equation is the absolute heart of the whole process. It says the curvature equals the moment, M, divided by 2 things. E is the stiffness of the material itself. Think about the difference between steel and, say, rubber. And I is all about the beam's shape. A tall, skinny I-beam bends differently than a solid square one. Together, that EI is the beam's total resistance to bending. This one elegant formula, it's the engine that drives all of modern structural design.
So let's bring it all back from the math and the diagrams to the real world. Why does cracking this code matter so much?
because it's what allows us to turn a drawing on a piece of paper into a safe, reliable reality that we can all depend on.
Because they can use this knowledge to predict the elastic curve before a single piece of steel is cut, engineers can guarantee that a bridge won't sag, that a floor in an office building won't feel all bouncy, and that a skyscraper can sway safely in the wind without any problems. It is the hidden science that keeps our world standing.
So when you look at this bridge now, you're not just seeing concrete and steel anymore, are you? You're seeing a whole collection of perfectly calculated elastic curves. It's a symphony of controlled smiles and frowns, all working together in perfect harmony. These are the invisible curves that keep our world standing.
So the next time you walk across a bridge or stand on the top floor of a tall building, just take a second, look around, and ask yourself, what other invisible forces, what other mathematical rules are holding up the world all around you right now?